Hello students, welcome back. It turned out there was not enough time for me to squeeze in another full proof at the end of the previous video. So let's start afresh. We had been talking about the algebra of matrices, especially the algebraic rules in regards to matrix multiplication. This is the definition of the matrix multiplication, and please key upon two things here. One is n, size m by n matrix, n by p matrix. The number of columns here and number of rows there must be the same so that we have the same dimension of row vector and column vector to multiply and take the scalar product as you see here. The second is index j. ij, jk, they have to be the same because j is running from 1 through n to make this scalar product work. J equals 1, so a1, b1, j equals to 2, a2, b2, j equals to 3, a3, b3, and so on, all the way up to j equals n, a n, b n, and then add them all together. That's how you get the scalar product there. So in the end, what do we get? Those two important numbers, n and j, both disappear. mn and p, eventually giving me mp, n disappeared. And here, ij, jk, in the end we get ik component. J disappeared. We used that in order to prove this associativity, which was, as a matter of fact, the hardest of the bunch. Let's go to the next one, the proof for multiplicative identity. Okay, we have to prove a times I is a, and then also I times a is a, but the second one, I'm going to leave those to students because it's going to be pretty much analogous to the first part. So let's do only this one, and here's the proof. A times I. So A is aij, and the size of that matrix is m by n. So this expression is completely the same as just A, or kind of like this. Yes, same expression. This is A with A11, A12, all the way to AMN, and this is abbreviated into that form, aij with the size of m by n. And when there's no danger of confusion, I'm going to remove that and simply write as aij, which I will from the next proof on. Okay, all right. So this is A, and that's identity matrix I. So for identity matrix I, we use Kronecker delta, that's traditional. We do not use any other character. For B or C, we don't do those. We use delta ij, and then if you look at the Kronecker delta, then what do you have? You have ones in principal diagonal where number of rows and columns are the same. We have 1, 1 entry, 2, 2 entry, 3, 3, 4, 4, 5, 5, all the way to n entry. Those are 1. Everything else, 0. So this is a conclusion. When two indices are the same, we have 1, otherwise all 0. And that's what we use, delta jk. So ij, jk. And then how do I set up the scalar product? Aij, I didn't highlight these yet. I just missed it. Aij, delta jk, ij, jk. So that's how you get the scalar product set up. And then we have mn and n, all the square matrices, all the identity matrices are square matrices. So we have to have nn. So we have mn, same size as the original. Okay, all right. And now let's do this computation. Please remember, this is Kronecker delta, which means when these two entries are the same, we have 1, otherwise all 0. Another reminder, yet once more, you see, we have 1s for diagonal, otherwise all 0. So, same row, same column, 1, otherwise all 0. Okay, that's Kronecker delta. And let's apply that here. Delta 1k, that's 0. Delta 2k, that's 0. Everything is there except for this delta kk. And that's 1. and everything else is all 0. All these are 0. All these are zeros. And all these dot dot dot, they have to be all 0 because all the diagonal entry is 1, everything else is 0. So what do you have? Only this term. So AIK, that's the only one that left. And then, just a reminder, the size of the matrix was Mn. So we have just AIK. What's this? Same as the original, except the choice of character. Instead of AIJ, we got AIK. What's the difference? Nothing, because just put them all together. Case running from 1 through n. Then you're going to get all the entries of the matrix A. So we ended up with A times I is equal to A. Key, express those in terms of the scalar product form, the main tool that we use all the time. And then the index structure is ij, jk. J's are common. See, that's always the case. And then just apply the property of the identity matrix. Unless j and k are the same, all 0, all killed. When j and k are the same, j is running from 1 through n, so the only thing that survived is delta kk, that's 1. So this one survives, everything else is 0. So what do we get? We get AIK, and put that as a matrix for arbitrary IK entry, and that's the same as the original matrix A that we started with. I'm gonna leave the other as as your own exercise, and let's see. The only thing that you have to worry a little bit about is number 1, order of multiplication, no big deal. Number 2, size of the matrix. Okay, that's a bit of a deal, but I guess you can handle that. Next, how about the distributive law? Okay, all right. Even though we have 3 matrices, this is a lot easier than associative law. Why? In that case, we have to consider Mn and then Mp and then Pq, the size of the matrices and the indices ij, jk, kl. That was rather complicated, but not in this case. It's going to be much easier. Indeed, we only have basically m by n and then n by p. Here in this proof, I just skipped all those matrix sizes. Okay, let's just do it one more time. M by n matrix, which I am highlighting in red. Oops. And then this one is n by p matrix. Okay. And then this one is, let's see, mn and p. These two are the same, but they disappear. So this is m by p matrix. What about the indices? ij, jk. Okay, let's just write the size of the matrix just once, because after that is done, these are just matrix additions. Additions, really, it's much easier to track down the size, so let's not worry too much about size of this matrix anymore. Okay, let's recap this. This is matrix A, and size is m by n. This is matrix B, and size is n by p, and then add it up with matrix C with the same size n by p. So this one is actually B plus C. And look at the size, mn and p. So we have size mp. Easier half. Now let's go to a little bit more difficult half. This is ij entry, and these jk entries. So jk entries of b plus c, and for b, bjk. For c, cjk. Because addition, you can simply add of each entry, so you don't have to worry too much about what kind of entries to select. ij, jk, and that's about it. And then what do? We simply apply the distributive law for addition here. Distributive law for real number arithmetic, excuse me. Distributive law requires both addition and multiplication. So distributive law for addition doesn't make any sense. Distributive law for real number arithmetic, because now if I go down to arbitrary ik entry, each entry is a real number. So all these are real number arithmetic. So we can separate by distributing aij around. So here we go, this plus that. And then what about those sigmas? Those sigmas are just a bunch of addition, so it does not matter which order we add them. So again, no problem there. Addition is commutative and associative, no problem there. And how about this? The summation, ij, jk. Why? That's matrix multiplication, A times B. And then what do you have here? ij, jk. Oh, that's another matrix multiplication, A times C. That'll complete the proof. So we don't have too many different sizes of matrix. So Mn and P, just do it once, so that's not too much of a deal. This time it was a deal, but this time not too much of a deal. So you don't have to worry too much about those sizes. But as for the entries, as for those indices, always pay attention to these. Matrix multiplication, so ij, jk, j's are common, and in the end they disappear. Okay. How about the other distributivity? Okay, this time I'm not going to bother with all those matrix sizes. So this is m by n matrices put together. This is m by p. Total m by p, and that's about it. And here's the proof. Let's see, can I put everything in the same viewing window? Okay, I just did. Barely, but I just did all right. So what do we have? A plus B, so aij plus bij, times c, so cjk. What's the structure? ij, jk, because we have to do matrix multiplication. ij, jk. So this is ij term, jk term. And what do you do now? This is scalar product, so summation of ij, jk, all those, and then apply the distributive law for real number arithmetic. aij timescijk, bij times cjk. ij, jk, so that's matrix multiplication, A times C. ij, jk, so that's multiplication, B times C. Let's go back to the definition of the matrix multiplication. Two key things. Number one, sizes, Mn and P, generating MP. That was simpler, so we talked about it already in the main portion. But here in optional advanced topics, let's do one more. Indices, ij, jk. ij, jk, j is common, and then in the end they disappear. This is ik term. Okay, remember that. One more, two more actually. I think we can do everything here. All right. How about this identity? A times BC is equal to AB times C. Okay. A times matrix multiplication first. So this is matrix multiplication, Bij, Cjk. Ij, Jk, J's are common. And then we have scalar multiplication, of course. Ij, Jk, and then we have summation, J is going from 1 through n. And then what do? We simply multiply scalar A using the associativity rule for multiplication. And we can multiply, but instead of calculating this multiplication before, we can calculate this multiplication before. The multiplicative law for the associative law for multiplication in real number arithmetic. But still, in the end, what do we get is matrix multiplication, Ij, Jk. Ij, Jk. So this is scalar multiplication, A times matrix B, and this is matrix C. So this one is small a times capital B, yeah, scalar multiplication, and then matrix C. This one's similar. A times matrix multiplication B times C. So how do you set up? Ij, Jk, and then this is scalar product, summation of Ij, Jk, Bij, Cjk. And then we just multiply by A, the scalar, and apply appropriate algebraic rule in the real number arithmetic, associativity and also commutativity. Switch the order of multiplication, not just A times B times C, but you see A times C first and B later, switching the order as well. Anyway, so Bij times A times Cjk. A times Cjk, this thing is actually scalar multiplication of the matrix C. So A times C is here, and then this is matrix B. Look at the index again, Ij, Jk. Do you see this is matrix multiplication? J's are common. Okay, all right. Final rule, the transpose rule. AB transpose is equal to B transpose times A transpose. How do we do that? Well, let's go with the definition of this matrix multiplication. Do the same thing. Pay particular attention to the index Aij, Bjk, Ij, Jk. J is common. And then transpose, so you have to flip, switch the order of those indices. Row becomes column, column becomes row. Ready? Let's go. Okay, Aij times Bjk, so that's matrix multiplication AB. And then we're going to take this transpose later. All right, let's do matrix multiplication first. Scalar product, so we have the summation. And then look at the index, Aij, Bjk, Ij, Jk. J is common. All right. Now, shall we take the transpose? Okay, what does a transpose do? Row becomes column, column becomes row. That's basically it. So please note that everything changed. A, Ji, B, Kj, you see. Row, column, all those indices flipped upside down. All right, now that we took this transpose operation to switch the order, and this matrix multiplication order is broken up. Here we have Ij, Jk, J is coming one after another, eventually canceling each other out. That was the nice structure of matrix multiplication, but that's screwed up here because of this transpose operation. So how do I mend it? We just apply the commutative law for real numbers, not matrix, for real numbers. Aji times Bkj, those are real number arithmetic, so we can switch the order. Bkj times Aji. So what do you get? Kj, Ji. Kj, Ji. I'm in a good setting? Yes, we are. This is a good setting for matrix multiplication. Look at the index again. I highlighted in red. Kj, Ji. One after another. Here it was good. Ij, Jk. It was good. Ij, Jk. But the transpose here screwed it up. So J's are separated. But that's okay. If I switch the order of multiplication in real number arithmetic, it's okay. We have Kj, Ji, and then we can separate. What do we have? Bkj. What is this matrix? It's a transpose because we start with Bjk and then switch the order of indices. Row became column, column became row. So this is transpose of B. And this Aji, that's also the transpose of A. So we got what we wanted. This thing over here, Bkj, is transpose of B. And this one over here, Aji, is transpose of A. The transpose is actually flipping over. We flipped over here, but then again, that prompted us to change the order of multiplication because we have to get correct structure of those indices. And then once we got those matrix multiplication again, we can note that this is a transpose again. That completes the proofs of all these, and I covered as quickly as I can.